Hello and welcome back to the lecture on applied econometrics. We have been talking about the probability distribution for discrete random variable and continuous random variable. Now, we need to talk about couple of more functions, and these are called probability mass function or PMF, as we famously call it, mass function PMF, and probability density function or PDF, probability density function. And this PMF is a term that we use for discrete random variable, and for probability density function we use continuous random variable. Okay. So, we are just going to explain what is the probability mass function and probability density function. So, essentially we spoke about this before actually without specifying the names. Essentially, when we convert the frequencies into a probability, we use certain formula to convert that, right. So, we have seen that, remember the example we have given for female labor force participation. So, we sort of created a formula, right, and that formula actually explains, given a certain family income, what would be the female labor force participation. Okay. Now, that formula for when we use in case of discrete random variable, we call it probability mass function, and when we use in case of continuous random variable, we call it probability density function. So, we will explain this term mass and density, how they are different when we just do couple of examples, and we will see how we are actually using these functions. Okay. So, let us do an example for probability mass function, or for a discrete random variable how we constitute the probability mass function. So, let us say we are talking about a coin toss, our old example, very common example, coin toss. So, again we are tossing, so let us say example 1. So, you are again tossing 2 coins, and when you are tossing 2 coins, you are getting the events. So, let us say probability of head equal to 1, we already know. So, that is 1/4, and let us say probability head equal to 0 is 1/4, probability head is equal to 1 is equal to half, and probability head is equal to 2 is equal to 1/4. We already know that, we have done this example several times, and there could be no other value. So, we can write is equal to 0 otherwise. So, you sort of talk about all the values of the variable along with their probabilities. So, this is the idea. So, value of the variable along with this probabilities, value of the variable along with this probabilities, value of the variable along with the probabilities. So, you basically used a formula to convert that, right. So, you basically considered that 2 coins are unbiased, they are independent events, and that is where you sort of get the probability for these events, right. Now, let us do another example. This is a simple one. Let us do a little complex, and let us say I really do not know the probability of head occurring. Okay. And my random variable here, the second example, my random variable here is that, let us say, so basically you are repeating the event until you get a head. Okay. So, outcome observations until you get a head. So, your random variable is basically you sort of do this experiment, you keep on doing the trial unless and until you get a head. Okay. And let us say for this coin, since you do not know probability of getting a head, let us say is equal to p. Okay. So, that is basically because this time, since you do not know about the characteristics of the coin, you do not know if it is a 0.5 or whatever. Okay. So, you just simply denote the probability as p. Now, let us say you get a head, and then you will have the probability p, simple. But if you do not have a head in the first trial, so let us say you have a tail first and then a head. So, then in this case your tail is going to be, so probability head and probability tail, this is the only 2 possible outcomes. So, tail is going to be 1 minus p, and then you have a head. So, that is going to be 1 minus p into p, and you can sort of write it down like, let us say this you are basically indicating it as a trial, probability of trial. So, this is the first trial, and this is a second trial, let us say this is the third trial, okay, the third trial and so forth. We are just going to write it down. So, let us say in the third trial you are going to, you see that there are 2 tails and 1 head, and you basically have 1 minus p into p, okay, or basically you can write 1 minus p square into p. In the next trial you will have probability t is equal to 4, and the value is going to be just following the same logic 1 minus p cube into p, okay. And if I sort of get a generic formula for this, I will write. So, basically if I have like let us say n number of events T n, so then I will have the value will be 1 minus p n minus 1 into p, right. And here what I have done is I have constituted a function. You see that I have actually got a formula for us to sort of put any number into that and get an output, right. So, this is the function I have just created, this is the function I have just created, all right. Now, this is my probability mass function, and then I will write down this function is valid if, so my n can only take integral values. So, I can have sort of 1, 2, 3, 4 whatever number of trials, but I cannot have 1.5 number of trials. So, if n is equal to 1, 2 or dot 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 whatever, and let us say it is up to m I have defined, and 0 otherwise, 0, write down 0 otherwise, okay. So, it means that within this range I can say I can allow the coin tossing up to m number of times. So, then or it could be infinity also, I can allow the coin tossing up to infinite number of times, but I cannot allow 1.5 trials because that is not simply possible. So, that is the reason I will write 0 otherwise. So, this function that the function that we have derived, that actually represents the probability mass function. Now, going back to the previous example, if we sort of plot it, we can also plot it. So, if we plot it, we can actually see that let us say the probability values 1/4, half, and I will just explain why did we plot it. So, for 0, 1 and 2, we will have these values, this and this and this, okay. So, this way we can actually sort of understand the probability, the concept of probability mass function, okay. So, these are the 2 examples we have done. Now, let us actually try to do a probability density function. Let us try to understand how do we understand a probability density function. Now, we have said that it is for a continuous random variable. Now, if I have a continuous random variable in the first place, so I will see let us say I have a continuous random variable and I have my y here, I have x here, and usually we know that it will look something like this, let us say a curve. Now, always if I have to get a probability, I will try to get the area under the curve, let us say. So, if I have to get a value, the probability, let us say I will get the area under this curve, and I want to get a probability value between a and b, and I will get the area under the curve where my 2 limiting values are a and b. Now, I will explain to how do you obtain this actually in when you do a problem, but before that, as I said, it is very important that we familiarize ourselves with the concept of probability density function, okay. So, we can also write down, we have seen this probability, let me write down probability that x lies between a and b is going to be some function, okay, f x dx a to b. We have already said that when we explained the concept of probability distribution for a continuous random variable, but here we have to first understand the idea of probability density. What is a probability density and how is it different from the, when you say that it is different from the probability, how is it different from a concept of mass, let us say, okay. Now, when we did this example, here, this one, let us say, when we did this 2 coin tossing example, we saw certain values, certain probability values for each of these different outcomes, okay. we may call it a packet of probability. Okay. Also, we had this example here which we did previously, this one, and if I actually draw if I plot it, so let us say I have value, this is the outcomes of, this is the values of x 0, 1, 2, 3, 4, 5, 6, 7, 8, let us say 9, 10, 11, 12, and I have, if I get the probability values here. So, this is 0 I do not have value, 1 I do not have value, 2 I have a value which is 1 by 36, let us say this is, let me use a different color, this is 1 by 36, 3 is 2 by 36, 4 is 3 by 36, 3 by 36, 5 is 4 by 36, 6 is 5 by 36, 7 is 6 by 36. Again this one is going to be 8 is going to be 5 by 36, 9 is going to be 4 by 36, 10 is going to be 3 by 36, 11 is going to be 2 by 36, and 12 is going to be 1 by 36. Okay. So, if I just now use a different color, it's looking pretty messy. So, I am going to have for 2, I am going to have this point, for 3 I am going to have this point, 4 this point, 5 this point, 6 this point, 7 this point, again coming back to 8 this point, then I am going to have 9 this point, 10 this point, 11 this point, and 12 this point. Okay. Now, if I sort of draw these lines here, the strips. Okay. So, these are the probabilities for corresponding values, all right, and these I can call a probability packet. Okay. Now, this is possible, it is possible to get this kind of distinct probability values for each of these value of the observation, because of the reason that you have these values discretely available, right. You cannot get this kind of values for a continuous random variable, and the reasons you have explained why. Now, how you can get a value for a continuous random variable? So, I will give you an example to actually explain this, how we can actually get the values, and here what we do is we actually get a distribution. Okay. We actually get the area of under a curve, and let us say the example that we are giving, let us say the temperature in Kharagpur, let us say it can vary between say 10 degrees Celsius to 30 degrees Celsius, let us say. And what you can do is, let us say it is like the temperature is equally distributed across the year. So, all of this so it is the line is parallel to x axis, and if I want to sort of calculate the so the area under the curve is going to be always 1, because it is representing the total probability, all right. So, this is 1. Now, the thing is here I cannot really have value for say a particular say 10 say let us say 18.5 degrees Celsius, I cannot get a value, but what I can get, I can always get a value between 18.5 and let us say 20.5 degrees Celsius, let us say. We can always get the value for an interval, we can get a value, okay, but we cannot get a value for a specific temperature. Now, to sort of conceptualize the idea of density. So, here how we calculate it is like the area under the curve we know is 1. So, 1 is going to be for the rectangle, it is going to be the base, which is like let us say 20 here, 10 to 30, 20, and I have certain height. Okay. So, height is here. Now, the height h is going to be then 1 by 20, which is basically 0.05. Okay. So, this height is known as the probability density. Now, note that probability density, the height is actually not the same as probability, okay, because depending on the length of your base, your height, the value of height will actually change, and you may have the probability density more than 1 often, right, depending on what value your base has. or it could be very small either. I mean, either both are possibilities. Now, so you need to be mindful about the difference between a probability density and the probability. So, when we plot a probability mass function, we only talk about the probability. So, mass of the probabilities that you sort of get, but here you don't get a you don't use probability, but you use a density. It's a relative sort of idea where you are dividing basically the total probability by the base of your of your distribution. And that is the reason we have to keep in mind that for continuous random variable you always use probability density, which is not probability. Okay? And you see when you plot normal distribution and so forth, you will be using probability density. Okay? So, that is the idea of probability density. Now, the example that I have given is that there I have like continuous temperature distribution. Now, it could be like or rather it is a sort of there is no gradient, it is always the distribution of the temperature is across the year is same. It may actually vary also, and I will sort of give another example. So, the same example let us say, but here I will vary the the distribution, the weight of the distribution across the different months, and let us say I have the Kharagpur region is mostly summer. So, let us say I will have something like this. Here let us say it is let us say 10 degrees Celsius to 30 degrees Celsius. Let us say we have the highest temperature goes to up to 30 degree. Now, here what we do is now given the fact that I am assuming that the temperature is mostly summer. So, I am basically giving more weight here and less weight here. So, this is basically the area basically you get, and here also you can in the same way you can calculate the area of a strip. Let us say I want to know the area between these two. Let us say I want to know what is the temperature, what is the probability of the temperature being 20 to 22 degrees Celsius, let us say. Okay. So, these are all doable. It is basically a simple geometry. The example I am sort of giving you is really a simple example, and we can sort of like use this area of right angle triangle here. So, you can basically calculate, let us say the area of the the total area of the curve is going to be half of base is basically 20, 30 minus 10 into some height. And if you want to sort of calculate this area, let us say I am first interested in this area. Let us say how many, let us say I use for the years of calculation, I use this one. So, I want to know what is the percentage of the year that the temperature is between 10 to 20, and we know how we calculate the area for right angle triangle. So, it is here it is 10 into some h prime, this is h prime, this is h. Now, we know that h prime and h is actually it is some value you multiplied by the base, right. So, it is going to be half 10 into some 10 k. The ratio is going to be constant for all the different right angle triangle. It is basic class 10 math, 20 into 20 k. Okay. So, you cancel k this. So, 100 by 400. So, which is basically 25%. So, basically it means that in Kharagpur region for to get, so in 25% percent of time over the year you have temperature which is basically between 10 and 20 degrees Celsius, whereas for 20 to 30 degrees Celsius you have the rest 75%. Okay. So, this is how you calculate probability for a continuous random variable. Now, these are the simple examples. I have used simple geometries. Of course, when we actually do problems, the curves are not really that simple. So, you can really have complex curves of different contours. So, we will see either we have to use integral calculus or we have to use standard tables, and luckily fortunately for us we have many standard tables like Z for Z distribution, T distribution, which we will be using. We do not have to really do use calculus, but we can simply draw these values from these tables, and we will see how we can do that. Okay. So, with this we kind of at the end of this lecture, and last I will just talk about one more concept, and that is cumulative distribution function or CDF. So, we have learned PMF, we have learned PDF, and now we are talking about CDF. Now, as the name suggests, the cumulative, it is quite intuitive. Okay? We should be able to make sense what we mean by cumulative distribution function. Now, basically you add up all the probabilities, for a given value of the random variable, you see what, what is the sum total of the probability for that random variable before that particular value. Let us say I want to know the, CDF. So, I will define CDF as like this. So, let us say CDF is going to be something like probability of x less than a. Okay. So, all the values are adding up to a, and we sometimes represent it as, or we write it as a function. This is also represented as function of a. Okay. So, the moment I write this, the moment I say that this representing the CDF, so essentially it means you have kind of summed up all the values up to the value a. Okay. And this is actually equally true for both the PMF as well as PDF, or continuous random variable as well as the discrete random variable. So, if I write, let us say probability of x less than equal to 25, you will simply write is equal to basically f of 25. So, the same thing. Now, I will ask you a question. Okay. So, I have been talking, now it is my turn to ask you a question, and let us say I ask you for a continuous random variable, what would be this value f of infinity. So, basically we know when I write f of something, that is basically the CDF. Okay. So, if I ask you what is the value of f of infinity, what would be your answer? Pause for a moment and think, and then I will answer it. I hope you got the answer. So, this is going to be equal to 1, because the moment I say infinity, I am going from minus infinity to all the way up to plus infinity. So, I am basically covering up all the possible values, and basically I am covering up all the probabilities for all the possible values between minus infinity to plus infinity. So, that means it is always going to be 1, and if that is the logic, then what is going to be for this, what is going to be this value, f of minus infinity. So, if f of minus infinity, if you want to think for a moment, f of minus infinity is basically, you have not yet started, basically you are in minus infinity, you have not added up any number, right. So, that means it is going to be 0. Okay. So, this is something you need to remember, that f of infinity is equal to 1 and f of minus infinity is equal to 0. Of course, we are talking about a continuous random variable. Now, given this, how we can write the a continuous random variable, the distribution of a continuous random variable using the idea of CDF. So, we can write it is always going to be 0 f of a to infinity. Okay. This is something we can always write. Okay. And as I said, it is same for discrete random variable as well. Now, if I say that, let us say, again let us go back to the example of this coin tossing, this one, and here I ask you that I ask you f of 1. So, which means I am asking you head could be 1 maximum. So, that is the maximum. So, it means when I write f of 1, let us go back to where we are writing. So, here f of 1 is going to be what? Probability of head is equal to 1 plus probability head is equal to 0, right. So, if I sort of write down the probability values, I know probability head is equal to 1 is half and this is 1/4. So, together they will make 3/4. So, that is going to be my using the CDF I can get the value. Okay. So, this is basically the idea of CDF, and we may use the concept of CDF time and again. So, this is basically the basics of probability distribution for discrete random variable and continuous random variable. Now, in the next lecture, so this is we will end here, and in the next lecture we are going to talk about expectation rules, variance and covariance rules, which we are going to use going forward, and what is an expectation. Most importantly, we sort of need to familiarize ourselves with. With that, done, we will be now, after that we will be talking about different types of distribution, standard distributions that we will be using all throughout our lectures. So, with that we end the lecture here. Thank you.